Okay, as you know, there'll be a take-home final, right? All right. Um, let's see. My computer was rebooted, so I gotta get everything back up again.
It got really cold outside today.
Yeah, it's crazy. Did not enjoy it. Yeah, when's summer coming? This is just crazy.
I'm so happy I got my second vaccine this morning, but Paige and I went over
Okay.
and it's like we had to wait outside. It's like,
Ah, freezing to
no wonder
death.
it's
Yeah.
cold.
Yeah, where did you get it?
The Lynchburg City
Oh, good.
Eagle over on Candler's Mountain Road.
Yeah,
So,
yeah. Cool. Do they like ask for a bunch of ID or no?
so I brought my passport both times. They
Yeah.
didn't ask for anything though.
Ah, yeah, okay.
So, and the second go round was even easier because I just handed them my card
Yeah,
and
the
they were like,
card.
hey.
Yeah, yeah, I got you. Okay. That's
So,
cool. Yeah. Ah, yep, I'm done with mine too. It's almost 3 weeks now since I had the second shot.
nice.
Oh yeah, it's great. Okay, everybody. Let's get started. So, in the video from Tuesday, that lecture was about adding angular momentum the way we've been adding it, right? We already went through, I think, the first example that he went through, which was adding two spin 1/2 particles, right? And let me share the screen. It's not sharing. Hold on, give me a second. Sorry, my screen's all messed up now. Okay. Um, this is where we left off, where we ended up with a triplet state and a singlet state, right? Where we were adding to, when we add two spin 1/2 particles, we can have, S1 plus S2. So if S1 is a half and S2 is a half, then we have to, you can have a total spin of S1 plus S2, right? And S1 plus S2 minus 1, right? And then you could also have S1 plus S2 minus 2, etc. But in this case, you could only go to the minus 1, right? So you could only have S total is equal to 1, which is S1 plus S2, or S total is equal to 0, which is S1 plus S2 minus 1, right? Okay. All right. And then we saw that there are, well, I think we weren't quite done with this particular case. So I'm kind of roll back, because what we're looking at is can you prove that these states are eigenstates of the S squared operator? I'm not sure we did that. It doesn't look like we did. Yeah. Um, so we got these states by actually applying our S minus, right, to other states. That's how we got this singlet and triplet states, right? But I mean, the whole idea is just that you're having, S1. Oh, shoot, hold on. There we go. S1 is 1/2, and S2 is 1/2, and then the total S total, right, is going to be S1 plus S2, S1 plus S2 minus 1, S1 plus S2 minus 2, dot, 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 until you get to 0. And it doesn't go past 0. Yeah? Okay. Now, if you notice, what we had to do, we had to apply these lowering operators on this state. So we figured out we had this state, and we used the lowering operators to see what would we get if we lowered that state by 1. And that's how we ended up with this state here, the 1, 0 state, and the 1, -1 state, right? And that's how we figured out these coefficients that were in front of them, right? There's a coefficient here of 1, and there's a coefficient here of 1. But you don't want to have to apply the s plus minus states, right, to figure out what when you're adding angular momentum, right? If you have two particles of spin, say 1/2 and 1, you don't want to have to apply rising and lowering operators to them to figure out what the states are and what the coefficients are. And that's where those Clebsch-Gordon coefficients come in, right? So in general, we can write the Clebsch-Gordon equation coefficients, which express our total state Sm, right? So S is the total spin, and M is the total, Z quantum number, Z component quantum number. Right, and it's equal to M1 plus M2, right? Okay, it expresses this state as a linear combination of the states that look like this, right? So where you have a state that looks like S1 M1 and S1 M2, right? So let's just think about, and I haven't written anything here for a reason. So give me a second. I want to make sure that we understand what this notation means, right? So I know we've had a lot of different notations. Okay, so let's look at the example we have up here. Sorry, up here. I'm going to take a look at this guy. So this is shorthand for S1 equal 1/2, M1 equal 1/2, S2 equal 1/2, M2 equal 1/2. That's what that's short for, right? And similarly, if I had this guy up, down, that's short for S1 equal 1/2, because we are in this case here, S1 equals S2 equals 1/2. We're adding two 1/2 spin particles, two spin 1/2 particles. So this is short for S1 equals 1/2. Oh, there goes that air raid siren. Fun times. Yeah.
Worried about that?
What?
Should we be worried about that?
No, that's just a test. It's a test. It's every.
Well, I can hear it from the apartments.
Yeah, I'm hearing it from my house.
That's insane.
Yeah. Yeah. I don't think it's some kind of test because they do this here and there. I can't imagine it's not anything. I don't think anyway. I thought they tested it on Tuesdays at noon or something.
They emailed yesterday that they were going to test it.
Oh, there you go.
And
Okay.
I think in addition to that, they send out the emergency emails and texts.
I got you. Okay, so they're testing this emergency system. I just thought it was on a particular day, and I was wrong about that. Anyway, okay, so here we have, so basically this is shorthand for this. Remember, this is the shorthand for S1 for this first spin. This is the shorthand for the second spin, right? So this notation here does not automatically tell you that it's a spin 1/2 particle, but usually these ups and downs arrows are not used for anything else except for spin 1/2 particles. Anyway, so this guy here is shorthand for this, and this guy here will be shorthand for S2 equal 1/2 and M2 equal -1/2.
Wait, wouldn't it still be S1?
Here? Not here.
Yeah, well, unless the other one, because it says SM equals S1 M1 and then S1 M2.
Oh, wow. That was stupid. Thank you. Yeah, no. It's M2. Yeah. Sorry about that. Yeah, that was lame. Yeah. So this one here is S1. This is M1. This is S2, M2, right? Same thing here. S1, M1. S2, M2. Okay. So these up and down arrows are shorthands for that. But that up down arrow is really not used for any other system because it doesn't really tell you what S is, right? So if you had an S equal 1 particle, a spin 1 particle, then it would, you couldn't use this notation because it wouldn't tell you what S1 was. If S1 was 1, it wouldn't tell you that, right? It'd be confusing and weird. And if you had an S equal 1 or a spin equal 1 particle, right? The M values for a spin equal 1 particle are not just 1/2 and -1/2. Can anyone tell me what they are? So if you had a spin, just for an example, spin 1 particle. So that means S equals 1. What can M be? Hello?
1, 0, and -1.
Yes. So we start, so it goes from -S and then by a factor of 1, right? So you add 1. So adding 1, I get 0. Adding 1, I get 1 until I get to S. So here's S, here's -S. And this one, of course, is -S plus 1, right? Okay, so the notation with arrows really would not make sense here, right? Like, so if you were going to make one of these kets, you would always use this notation. It's just this up-down arrow notation that is used for the spin 1/2. And that's always code for S1, always code for, spin 1/2, S equal 1/2. And then the up arrow is plus 1/2 for M, down arrows -1/2, right? M equal -1/2. So here we're going to write this ket and say we had the, S, M, right? We would write something like, 1 -1, or, for the 1, 0 state, right? Maybe you wouldn't have the comma, but, right? So that's the notation here that is for spin 1/2 is the only time that's used. Okay, it's not used for any other spin, just because you couldn't really. How would you denote this with arrows? Wouldn't really make a lot of sense, right? Does that make sense to you? Yeah. Okay. Anyway, so let's get back to the coefficients, right? The coefficients that end up in front of these things right up here that I'm showing, right? These coefficients. So you can see that the total M, and I was calling it MS, but we can call it just total M now, right? So the state that's written as total S, total M, that's here 1, 1, right? Has some sorry, this coefficient is wrong there. Sorry about that. This should be here. Is some coefficient times this, right? And that coefficient is 1. So this is the total S, the total M, written as a linear combination of, and remember this is shorthand for 1/2, 1/2, 1/2, 1/2. Okay, like here. All right. So there's some coefficient there, and that's what we're after. All right. So in general, the sum. Why can't my pen does not write today? Come on, sorry about that. Let me get the sum right. Better? Okay. With M1 plus M2 equal M, okay, of Clebsch-Gordon coefficients, which are have these indices M1, M2, M, S1, S2, S. This is a very fancy and kind of stupid way of writing these Clebsch-Gordon coefficients that are in that big ugly table that you saw in the in the video. Okay. It's just saying, hey, the total, the ket, right, the state that is written in terms of the total angular momentum mass and the total z quantum number m is some linear combination of these states, right, of the two single states, right, of the two single spin states with some coefficients, the Clebsch-Gordon coefficients. Okay. And up
Okay.
here, yeah, question.
All right. Because when I was doing, I was kind of confused by like what was going to go in the indices and how in the textbook they only had one indice per thing. I mean, in the textbook they had two of the. I'm sorry, I'm bad with the terminology. The line arrow thing. In the textbook they had two of them, but in the example shown it was only like one per.
Can you tell me what you're talking about in the book?
When he was going over the 301.
The 301. Wait, in the book or in the video?
In the book, I'm talking about the
Oh,
book.
I see. Yeah. I see that. I see the 30. Yeah, I see that.
Okay.
Yeah.
When he was going over in the video, it only had one of them per coefficient, but in this example, it had two of them, and I was kind of confused by.
Oh, okay. So yeah. Well, if I remember the video right, so I have a screenshot from the video too that I'm going to use in a second. But I think just remember that notation is probably this thing here, right? Where this notation really means this. See what I mean? Like this notation. Yeah. This notation.
Oh, I see now.
This notation. Yeah. That's why, like I said, the spin 1/2 notation is the only time that this notation is used.
Okay.
If you have another system, like I said, like a spin 1 added to a spin 1/2, you wouldn't use it. So yeah, it can be confusing. Okay. All right. So let's take a look at. I like the screenshot that he had of the Clebsch-Gordon coefficient better than what the book has. Although they're very, similar. It's just that the screenshot, the thing he had, I was out of a different, like a big book of things you can look up, like, all the Hermite polynomials, blah, blah, blah. And it was very, it was very clear what everything means when our book doesn't have that, which I don't like. So anyway, so let me get that. What's this supposed to be in a new layer? Oh, I just turned this one off. Give me a second. I'm going to make it bigger because I bet it's really small for you guys. Stop it. Sorry, give me a second. It's hard to work with. No, I want it bigger. Okay. All right, and now let's move it over. Okay. Okay, and then we're going to turn this off. Okay. All right, so let's take a look at the singlet state and the triplet state that we know already, and just verify that we understand how to use this thing. Okay, now in your book, if you care to look at the book at the same time, it looks the same, except it doesn't have this nice little explanation up here, this thing, which I like. I like having a reminder of what all these things mean on the table, right? So if you are inclined to write in your book, you could just write this little thing right in your book so that you always know what the coefficients are, or what all these numbers are, right? And you don't need this, right? This is just somebody decided it would be convenient to put the YLMs in there. I don't know. So it's just this, and then they don't make it really clear what they mean by this either. So in the book, they say it in words, but they don't write this out. So I would write this also in your book if you're not going to sell it back or something. Although you'd probably be helping whoever you got the book again after you. Um, but I just would write those two things down because it's just awful if you've forgotten and haven't looked at it for a while or something. Okay, so let's look at the singlet states that we have and the triplet state. So we have remember the form is total S total M is equal to coefficients times you know, the shorthand here, and I'm going to write it out. So this is 1/2, 1/2, 1/2, 1/2. So in other words, S1, M1, S1, M2. That's what that's shorthand for. And that's our first state. Sorry, I should have written this out. This would, this is 1, 1. Right, so just reminding you what it is. Right, so this is total S, total M. Right, that's what the notation is. And then our singlet state has this, which is code for this and this together. Okay, and then 1, 0, which of course is total S, total M, is equal to 1 over the square root of 2, right? Times, and I'm going to write it in both notations. So first I'm going to write in the up, down arrow notation. Up, down, and plus, down, up. And if you notice, Griffiths doesn't put the kets around these up downs. I just have always done that, so I just keep doing it. It's again just a shorthand anyway. Okay, so let's write out what it's shorthand for. It's shorthand for S1 equal 1/2, M1 equal 1/2, S2 equal 1/2, and M1 equal minus 1/2. And then plus the state that is S1 equal 1/2, because of course it's always going to be 1/2, and then M1 equal minus 1/2, and S2 equal 1/2, and M2 equal 1/2. That's the shorthand, right? That's what this means. You can see why the shorthand is used. But I would get in the habit of either writing this first and then writing this for spin 1/2. So you just remember what it is, because as soon as you move away from spin 1/2, you can't use this notation anymore. Okay. Okay. That's a second thing in the singlet, and then the third thing in the singlet is total S equal 1 and total M equal minus 1.
And this is for the 1/2, 1/2 equation.
1/2, 1/2. Yeah. So this is S1 equal 1/2 and S2 equal 1/2. So we're adding two 1/2 particles. The first example, we're just going over it again. We're going to write it down. We're going to look at the Clebsch-Gordon coefficients. Okay. So, and then this one is, the shorthand notation like this, which of course is just 1/2, 1/2, or, S1 equal 1/2, M1 equal 1/2, and times S1 equal 1/2, or S2 equal 1/2, M2. Oops, wrong. Thank you. This is minus. They're both down.
One more question.
Yeah.
Okay, I understand how to get the M values.
Yeah.
How how exactly, because I understand that S1 and S2 add up to get S, which in this case would be 1. But how is it always an even split?
What do you mean?
Like are S1 and S2 always like is it always like, are they always exactly half of S?
No, because S1 and S2 could be different. Like, for instance, you could have a spin 1 particle mixed, added to a spin 1/2 particle, right?
Okay, then
and then one of your states will be total spin equal 3/2, right?
all right, so right, okay.
So remember, right, when you want to know what your total S is going to be, your total S is going to be S1 plus S2,
Yes.
S1 plus S2 minus 1, comma, S1 plus S2 minus 2, dot, 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 until you get to 0, and then you're done, right? Including 0.
Okay. So how do we find what S1 and S2 are?
You're just given. So it's a question like, think about the hydrogen atom, right? The hydrogen atom has one proton and one electron, right? And when you want to know the total spin of the atom, you need to add the spin of the proton times the spin of the electron. And both of those particles are spin 1/2 particles. That's their fundamental nature, right?
Okay, so S1 and S2 will always be given to us.
Yeah, absolutely. Because it's a definition of the problem. Like, okay, did you want to add a photon spin with an electron spin, right? That would be a spin 1 plus a spin 1/2.
Okay, because
Right.
I
Yeah.
was kind of confused about where to get the S1 and S2
Yeah.
values on the practice problem
Right.
thing.
Okay. Yeah. Yeah. It's always given to you. It's always like, they may not tell you what particles you're thinking of adding, but they might say, add a spin 3/2 particle with a spin 1 particle. What are
Okay.
the states that are possible, right? It's always something that you're given. It's not like this comes out of the air. Now, if someone told you the particles, and you'd have to know what the particles spin are. Remember, that's fundamental to the particle, right? Like a graviton is spin 2. Right? So if someone told you to add a graviton spin to a electron spin, you'd be adding a spin 2 to a spin 1/2. Right? So you may have to know the spin of the particle. I mean, not on my tests or anything, because you can just look that up. But yeah, yeah. Someone will always be giving you those S1s and S2s. Got that? Okay. So remember, for our case here, right? For the spin 1/2 plus spin 1/2, the total S can be 1, which is S1 plus S2, and then S1 plus S2 minus 1, which is 0, and then we're done. Those are the only two possible things it can be, right? So here, all you can see the total spin is 1 in all of these states. That's what's called the triplet state, because of course M can be -1, 0, and 1, right? And then of course there's the S equals 0 state, 0, and then M can only be 0, right? And that one is the 1 over the square root of 2, up, down, minus, down, up, which in the other notation, the clearer notation, is S1 equal 1/2, M1 equal 1/2, S2 equal 1/2, M1 equal -1/2, minus S1 equal 1/2, M1 equal -1/2, and then S2 equal 1/2, and M2 equal 1/2, positive 1/2. Right. Again, just expanding this notation, which, like we said, is only good for spin 1/2 particles. Otherwise, it's just useless. Okay. Let's see if we can figure out the Clebsch-Gordon coefficients. Right? So again, we found all these, well, the book did, right? Found all these coefficients that you see in front, right? So notice, if we wanted to know what is the coefficient for this S equal 1, M equals 0 state, it would be 1 over the square root of 2 times this, and 1 over the square root of 2 times this, right? So the coefficient is 1 over the square root of 2 on this state, and 1 over the square root of 2 on this state, right? Or these two here. Better to look at. The coefficient for the total S equal 1 and total M equal -1 is just a 1 times those states, right? Because remember the equation, I'll write it down again. So we have the total S, total M is equal to this sum where m equal m1 plus m2 of the Clebsch-Gordon coefficients, which have all that crap on them. What is it? M1, M2, M, S1, S2, S. It's just a crazy notation for that giant table. And then times, of course, S1, M1, S2, M2, right? So if you look up here, that's exactly what we have here, right? The Clebsch-Gordon coefficient for this state is 1 over the square root of 2 times this plus 1 over the square root of 2 times this. So let's go to the table. Okay, first of all, what is the part of this table that I would use for adding a spin 1/2 with another spin 1/2? Where am I looking for that?
Can you say that again?
Where is the part of this table where I can get these things?
Oh, in the diagonal boxes. I mean,
Okay. Can you just tell me what part of this table, what part of this giant figure I put up here is where I would look for the spin 1/2 plus spin 1/2?
for the spin 1/2.
Mm-hmm.
Okay.
Is it big enough?
No,
It's not big enough?
I don't see where S equals 1/2 on this table.
Okay, so where you're looking always, and this is something that's not great on this particular table because they give you all the notation, but they're not telling you where the spins are, okay, that you're adding, okay? But the spins are the giant text, the only thing that's giant text up here. So it's like here, right? So that says, hey, this is where you're adding spin 1/2 to spin 1/2. This one here is if you want to add spin 1 to spin 1/2. This one here is where if you want to add spin 2 to spin 1, etc. And of course, this table, if you go look it up, there are, this is, let's see, is it leaving anything out that's really, I don't think it's really leaving anything out. It's pretty much everything you'd want to do probably on this table.
Okay.
Anyway.
All right. There's just one thing that
Yeah.
All right. In this,
Yeah.
it's saying like on the 2-1 equation, that's basically saying that spin 1 is 2 and spin 2 is 1. Right?
No, I don't know where you're talking. Where are you tell me where you're looking.
The 2x1 table.
2 times 1 table.
Right?
Yeah, 2 times 1 here. Yes, right. So this is basically S1. This is S2.
Okay.
Yeah, and it says times, but it really means combine, right?
All right.
Right.
I understand that, but then why are there some that have S equaling 2 and 1 on here?
So you're asking why are there ones that are like 2-1 or 3/2 1 or 3?
No. I like
Mm-hmm.
if from here, if J is in this example, J is S and big
J
M is
total S and total M, right? That's right.
yes. So in this one, it has where total S is 2, but S1 plus S2 equals 3.
Yeah, but remember, it's S1 plus S2, which is 3.
Mm-hmm.
Then another value you can have is S1 plus S2 minus 1, which is 2.
Okay.
Right? So there's
All right.
You have to go down the list. So if you look at this one, it's a good example. Here's S1 plus S2, 3. Here's S1 plus S2, 3. Here's S1 plus S2 minus 1, 3. Here's S1 plus S2 minus 2, 1, right? Etc.
Okay, so all right, I understand. So
but let's go back to our 1/2, if you don't mind.
Okay.
Okay, so if we go back to the 1/2, let's take a look. All right, so let's look at our thing up here. So this is going to be total S. total M, right? So that's what these are. J is used, and I'll tell you why in a minute, but let's just look at just those are total S and total M. All right, so let's look at total S equal 1, that's here, and M equal 1, right? Okay, and then we are told that over here to the left will be the M1s and M2s. Yeah? So here is the M1 and M2. Yeah? That makes sense? So M1 and M2, M1 is 1/2 and M2 is 1/2. So let's go back over here and look. Okay, yes, that is true. We already know that the S is 1/2 and the right, and the you know, the S1 is 1/2 and the S2 is 1/2. And then here it tells us the M is 1/2 and the M1 is 1/2 and the M2 is 1/2 right here, right? And it tells us the coefficient is 1, which indeed it is, right? Yeah. Okay. Let's look at this one. The S1 is 1. The total M, sorry, the total S is 1. The total M is 0. Yeah, that's the state we're looking at here. Okay, and then again, it tells us the M1 plus the M1 and the M2, right? So we have the M1, M2. So it's up, down, right? Up, down. And the coefficient is 1/2, which remember means 1 over the square root of 2. All the square roots are left off, right? That's what this up here is, right? And then the other one is -1, so down, up, right? Down, up. So up, down, up, with another coefficient of 1 over the square root of 2. Right? Okay. And then let's look at 1 minus 1. Okay, that's the other singlet. I'm sorry, that's the other triplet, right? We have S equal 1, total S equal 1, total M equal -1. The two states are down, down, right? So M1 is -1/2, M2 is -1/2, and we get a coefficient of 1, which indeed we have. Right? Okay. Last one is the singlet state, 0, 0. Total S is 0, total M is 0, and we get the M's are over here again, right? So we get a positive 1/2 on the M1 equal up, M2 equal down, here, or here if you like. And then a -1 over the square root of 2 on the state that is down, M1 equal down, and M2 equal up. Yeah.
Okay, last question.
Yeah.
I understand that big S is the total spin of the system, you know, the addition of S1 and S2. The only thing that I'm kind of about is how can the total spin, if its individual parts, be less than, like why does it increment down? Does it have to do with like the amount of, I don't know, I can't.
Well, so think about it this way. You know, you're combining spins, and yeah, that's a really good question. I'm not sure I have a good answer for that, because you're taking 2 spin 1/2s, and you can end up with a spin 0, right? A spin 0 state that acts like a spin 0 particle.
Well,
again, it's one of those quantum mechanical effects, right? Because that spin 0 state is a linear combination, in a particular way of 2 spin 1/2 states, right?
oh,
Yeah.
what if it's like the total addition is assuming that all of the particles that are spinning in the same direction. And when it goes down to 0, it's the assumption that all of the particles are like split in half, and half of them are spinning one direction and the other half are spinning the other.
Something like that. But remember, it's really not, they're not spinning.
Yeah, I know that, but like as like
But yeah. Yeah, well, I mean, look
a
at what the spin 0 state looks like, right? Look at the spin 0 state looks like here, right? It's got a spin 1/2, right? So here's one particle in a 1/2 state. The second particle is also in a 1/2 state, but in the other linear combination, right? So if you look at this, it's like these two cancel, although they're interchanged, right? So this is particle 1 and this is particle 2. This is particle 1, this is particle 2, right? But they have this thing where if you look, right, you have a cat that's up, a cat that's up and a cat that's down, a cat that's up and a cat that's down. And you can think of it kind of like they're canceling out, right? So
okay, so
I don't know if that helps, but
yeah, it does. Thank you.
it's a quantum mechanical effect, right? It's interesting because a spin 0 particle is a very different beast than a spin 1/2 particle. If you're in that singlet state, right? If two spin 1/2 particles are in that singlet state, they behave very differently, you know, as a single object. So kind of interesting, right? The hydrogen atom can be in that state. Although we're ignoring angular momentum. I'm sorry, we're ignoring orbital angular momentum. The total angular momentum of the hydrogen atom has to also include the orbital angular momentum, right? The Lm that we know from the spherical harmonics, right here. These guys. Right? So if you wanted the total angular momentum, you actually have to also use the Clebsch-Gordon coefficients, right? That's why this is J, because J is usually used. So the notation J is usually used for S plus L, right? So it's saying this is the total angular momentum spin plus, spin orbital angular momentum, spin angular momentum plus orbital angular momentum, right? So that's why that's J. That's just typical. So now if you wanted to find the total angular momentum of the atom, you would have to add, let's say you have it in the singlet state, you would have to add a spin, or you had it in the triplet state, you'd have to add a spin 1 with a spin whatever the angular, the orbital angular momentum was. So you use the same idea to get the total angular momentum of the atom. But I don't think we ever do that in this book. I remember doing it when I was a student, but I don't remember if we ever do that. I'm just going to look and see if we ever do that in the book at all. I'm just looking at the problems because they certainly don't do it in the text part of the book. Yeah. No. Yeah, I don't know. I don't know why they don't do it. Okay. So let's take a look at give me a second. So if I'm just trying to figure out which one I want to do. I guess we could probably just follow the book. So 2, 1. Yeah. All right. So let's just look at the book's example. So the book has an example where they're saying, hey, let's add. So let's add. Let me get a different color because it's getting a little monotonous. So let's add a S1 equal 2 particle and an S1 equal 1. And let's look at the state 3, 0. Right? First of all, right, this is the total S and the total M. Let's just write down what the total S can be. Right? So we have S can be S1 plus S2, which is 3. And it can be S1 plus S2 minus 1, which is 2. And S1 plus S2 minus 2, which is 1. Hold on a second. Just trying to interpret your book's notation on something. S1 less than absolute value of S1 minus S2. Yeah, I'm a little confused why there's no 0 here.
Does it cancel out?
I don't think so. That's interesting.
For that one, it would be 2, 0, 1 times 1, 0, 1. I mean, it would be
Yeah, well, let's consider on with it. Let's look at this and then just and I'll figure that other thing out in a second. So here's what we're after, right? The 3, 0, s equal 3, m equals 0, right? And then the m's are here. Yeah. And the coefficients are here. Right? And this first one, so this is where it gets a little confusing. For the 1/2, it was really easy. But remember, so the first particle is the 2, spin 2 particle. The second particle is the 1, right? So if you look here at the 3, 0 stars, here's where we're looking, right? The first one is M1, the second one is M2, right? So that would be, so the first coefficient is 1 over the square root of 5. And then the states are S1 is 2, so we have a 2. And then M1 is positive 1. Then the second state is S2 is 1, and M2 is minus 1. Right? And then the next thing is, I'm going to write it down here, plus 3/5, so that's square root of 3 over 5. Right? And then tell me what the state should be. What should the state be? What's the state for the first particle, the spin 2 particle?
2, 0,
2, 0, good. What about the spin 1 particle?
2, 1. I mean, 2, 0. I mean, 1, 0.
1, 0, there you go. Okay, now tell me the next term. Oh, yeah, okay. Anybody? What's my next term?
Square root of 1/2.
No, where are you getting the half?
I mean, square root of 1/5. Sorry.
There you go. Okay, so 1 over the square root of 5. Then what are the states?
2, negative 1,
Good,
and then 1, 1.
good. Yeah. All right, let's do one more. And actually, I figured this out. Give me a second. Oh, okay. That's not what I wanted to do, but whatever. All right. This actually doesn't go all the way down to 0. It goes down to the absolute value of S1 minus S2. Okay. So let's just think of since this dot, 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 let's think of the S1 half again, right? So for S1, equal S2 equal 1/2, we had S1 plus S2 is 1, right? And then we had S1, so it goes down to S1, the absolute value S1 minus S2, and S1 minus S2 is 0, right? So I hope that makes some sense. If you have the same spin, right? If S1 and S2 have the same spin, you're going to get a 0 spin. Otherwise, you can't get a 0 spin, right? So that this is just written a little wrongly. You got it? Okay, because the absolute value of S1 minus S2 is 0 in this case. So when you have the same spin, like look at the 1, 1 here. 1, 1, you do indeed get a total spin of 0. But if the spins are not the same, you never get a total spin of 0, because for our case here, we have S1 plus S2 is 3, S1 plus S2 minus 1 is 2, S1 plus S2 minus 2 is 1. But the absolute value of what is it again? S1 minus S2, because it doesn't matter which one is which, is of course 2 minus 1, which is 1, and that's the lowest it can be. So this is its lowest value. Okay, I hope that makes sense, because you really can't get a 0 unless you have the same spin on both particles, right? Otherwise, you're not going to get a total of 0 ever. Okay, so that's the only time you do, is when they're the same. Okay, anyway, let's do one more. Let's take a look at 3/2, 1/2. Okay, so we'll say another color here. So we'll get S1 equals 3/2 and S2 equals 1/2. Okay. First of all, let's figure out what the S's can be. So total S can be S1 plus S2, which is equal to, right, which is equal to 2. Yeah. So indeed, we see a 2 up here. And then S1 plus S2 minus 1, which is 1. And we do see a 1 up here. Okay. So let's figure out what the lowest one can be. That's going to be an S1 minus S2 absolute value, right? And that's just going to be a 1. So that's the lowest possible one. It's a 1, right? So when you're trying to figure out what total S is, first look at this, then you know what the lowest one is, and then look at this and start subtracting 1 from it till you get to this. Yeah? That makes sense? Okay. And when indeed look up here, we only have 1s and 2s for our total. Okay, let's figure out what the state, I don't know, 2 minus 1 is. So total S equal 2 and minus 1 is the total M. You guys tell me. Somebody got an answer for me? Yeah.
It would be square root of 3/4. 3/2 negative 1/2. 1/2 negative 1/2.
Good. Go to the next term, someone else. Go eat something. There's bagels. There's it. Figure something out, honey. There's a whole thing full of food in there. Someone else besides Jackson. I need coefficient. I got 15 minutes. I can wait. Jeff, Andrew, if you don't know what it is, what's confusing you? Ramen. Hello? Guys, come on, help me out.
I'm just a little lost, and I want to go over this with my tutor.
Okay. What about Jeff and Andrew?
I'm just lost too.
Okay, so where did I lose you? Do you not know where to look on the table? Okay, so in your book too, if this is too small, the book has the same table, although it's really, really small in the book. It has, well, does it have the same table? Yeah, it does. It does. Yeah. So remember, our spin, our first spin is 3/2, second spin is 1/2. So here's where you always look. S1 is always here. S2 is here. So this is, you're looking at this whole part of the table. And only this part now. Because we decided what our spins were. Okay. Now I asked about the state where total S is 2 and total M is -1. Okay. So I'm looking here now. So remember, that's like this in this format. See these little boxes that come up like this? That's where the total S and total M's are stored. Okay. So I'm going to do that in a little different color. So if I were going to outline them, it would be like, these are where the total M's and S's are. Okay. Okay. So if I'm asking for total S equal 2 and total M equal -1, that's right here. Okay. And then the things off to the side, like up here, I'm going to outline that in red. Those off to the side are the M's for M1 and M2. Okay. So if we look over here, I'm going to outline them. So here's 1. And last one here. And then the coefficients, the stuff that you are going to, the stuff that you're going to put in front of these states are everything else that's not outlined. Okay, so, and I better outline maybe that in a different color. So I'll put that in a light blue. So that would be a coefficient here, coefficients here, coefficients here, and coefficients here. Okay. And the 1 here is where we're looking, because we're looking for 2, 1, 2, 1. Okay. All right. This is the M1 and this is the M2. So what we have here, it's square root of 3/4 because it's a 3/4 here. That's coefficient. In front of the combined state, S1 equal 3/2, and then M1 equal -1/2. See, M1 equal -1/2. And then S2 equal 1/2, and M2 also equal 1/2. and then that coefficient is 3/4. So now we're gonna look down here. So one of you guys tell me, what is the next thing I need to write down?
It would be square root of 1/4.
Yep, 1 over the square root of 4, which is 2, but I'll just write square root of 4.
Yeah.
Times.
And then the brackets, 3 over 2.
Yep.
And then negative 3 over 2.
You got it.
And then 1/2 and 1/2.
Yep, you got it. Perfect. Yep. Okay. So I hope you see how that works. All right. It is confusing and awful, Clebsch-Gordon coefficients, right? And I guarantee you that you will forget how to read this table, which is why I was encouraging you to write this stuff in your book. And this, because your book does not do a good job of doing that for you. And even write, S1, S2 like this. Because then you know it's M1, M2 in these boxes. Yeah? Okay. All right, well, I think what we're going to do is we're going to end a little early, in about 10 minutes, because I'm going to start chapter 5. And I'd rather just start that fresh. Okay, we're just going to do a little in chapter 5. I'm going to do all of chapter 5 or anything like that because we only have 2 weeks left. So I'm just going to do a little of chapter 5 and I'm going to do a little bit, I think, of chapter 6. Let me just look at chapter 6 again. Yeah, give me a second. I think chapter 6 is perturbation. Yes. I want to do a little perturbation theory. So I'm just going to do a tiny bit of chapter 5. Just a kind of an intro. Okay. And then I'm going to do as much of chapter 6 as we can do before we end. Okay. All right, guys. We'll see you. Bye.